Hi everyone and welcome on board your really long-haul flight. On this channel we've put together a compilation of some of the most jaw-dropping moments from the sky. So now all that you need to do is find a comfortable place to sit, bring out your favorite drink, sit back and relax. Boeing and Airbus has both upgraded the engines to their 737 and Airbus A320 families during the last decade. The new engines that they fitted are a whopping 14 to 15% more efficient than the older ones. But now the CFM RISE engine promises to completely eclipse this performance. And strangely, we almost had this type of engine 3 decades ago. It's a really fascinating story, so stay tuned. In a recent video I discussed the surprising announcement that came from Boeing that they're not going to launch or even start designing a new airliner until after the end of this decade. Now, obviously, there's a lot of details about what this really means and how it's affected by Boeing's position relative to Airbus, and if you want to check that video out, I can link to it up here. But one important factor in Boeing's strategy is likely the expectations of a new technological leap or a step change in engine efficiency. As I said in the beginning, the CFM RISE is a central part in this, but to understand why, we have to talk a little bit about how jet engines have already been evolving over time. Now, if you compare the jet engines of older aircraft with today's, you will see that they are constantly getting larger in diameter. And that's because for a jet engine to be able to generate more thrust, it has to either push the air backward faster or push a larger air mass at the same speed. The latter option, more air, same speed, is the more efficient option. And this is why turbofan engines have been getting bigger and bigger by time, because that have enabled them to increase their bypass ratio, meaning that they use a bigger fan which can push more air around or bypass the engine core. However, a problem with making these engines larger and larger is that they are also getting heavier. Even so, modern high bypass turbofans are still more efficient than the older designs, despite the weight penalty that comes with encasing the whole thing in a bigger and bigger nacelle. But there are other ways for a jet engine to push a really large air mass backwards. One option that the engine makers and aircraft manufacturers were exploring in the 1980s was the prop fan, also known as an unducted fan or an open rotor. In their simplest form, open rotors work like turbofans, except that the fan is not encased in a nacelle. In order to have the necessary efficiency, thrust and a manageable diameter, these early open rotors had 2 counter-rotating fan discs. These fans had a variable pitch, unlike the fan blades on the turbofans that we have today, and that increased their efficiency further. A number of companies worked on these designs, but the ones that were developed the most in the 1980s were the Pratt & Whitney Allison 578 Delta X-Ray and the General Electric GE36. The Pratt & Whitney Allison variant built on previous research that Allison had done on a prop fan design for NASA. General Electric also based its design on NASA research and actually had the French engine manufacturer Snecma as a minority partner on the project. General Electric and Snecma were also partners in the CFM56 joint venture, and today Snecma is known as Safran, and of course the CFM joint venture is still ongoing. Now, the reason Pratt & Whitney and General Electric were developing these prop fans was because one of them would be chosen to power the Boeing 7J7, Boeing's planned replacement for the 727. Now, of course, technically the 757 was the 727 replacement, but it was substantially bigger and had a longer range than the 727 did. And this was appreciated, obviously, by many older 727 customers, but not everyone wanted to upsize to the 757. So Boeing was developing the 7J7 to be a bit smaller than the 757-200. Of course, today we know that this didn't happen. Boeing instead developed the 737NG by enlarging the 737 to replace the 727 and to compete with the then upcoming Airbus A320 family. But it's worth remembering that the development work on the 7J7 was quite far ahead when it got scrapped. Boeing never launched the project formally, but it discussed it with a number of different airlines who wanted to replace their 727s, DC-9s and even their earlier 737s. The 7J7 would make use of space-age materials and would have an advanced cabin layout and avionics. And by the way, Boeing also circulated pictures of a fly-by-wire cockpit with sticks instead of yokes. So what actually happened to this aircraft then? Well, it turns out that what actually killed it was the engines. In a way, open-fan engines were a bit too far ahead of their time, needing much more development and innovation. The Pratt & Whitney Allison 578 Delta X-ray was equipped with a gearbox to drive the counter-rotating fans, and there were some concerns about the reliability of those gearboxes at the time. Boeing eventually chose the GE36 partially because it didn't have that gearbox, but excessive noise was a huge problem which affected both of these designs. These engines were apparently even noisier than the low bypass turbofans that the MD-80 and the 727 used back then. Now, some believe that the noise problem was a bit exaggerated, but it's worth remembering here that today's CFM LEAP and Pratt & Whitney geared turbofans are much quieter than those old turbofans who the open fan engines were compared with. So today, they would definitely be considered as really noisy. And finally, another factor that didn't help these engines, or the Boeing 7J7 for that matter, was the fact that the oil prices dropped in the late 1980s. And with that, airlines became less interested in the idea of a new, noisy plane that would be more efficient but used radically new, unproven technology. So Boeing shelved its plans indefinitely. At the same time, McDonnell Douglas were also considering an MD-80 derivative fitted with either of these engines, but the airlines just weren't interested. So why are we discussing this now then? What has changed since those early designs that would make the CFM rise not only possible but also desirable? Obviously, fuel efficiency is really back on everyone's focus today. Boeing has come out and said that its next airliner will need to be at least 20% more efficient in order to be truly competitive. The prospects for truly great efficiency improvements in open-fan engines were obvious even before the 1980s, which is why their development continued even after Boeing and McDonnell Douglas shelved their plans in the late 1980s and 90s. And during those years of development, the engineers learned a lot about the technologies that could make open-fan designs really possible. And actually, this research was a process that worked great both ways. For example, General Electric worked on a composite fan blades for its all GE36 unducted fan that came in really handy for the GE90 engines that would later power the Boeing 777. And the same goes for the CFM LEAP engines for the 737 MAX and the Airbus A320neo. But then there was the question of noise. And immediately, this is where the French engine manufacturer Safran came with some fantastic news. In 2017 and 2019, Safran built and tested a new open rotor concept. This engine had a similar configuration as the GE36 unducted fan, but using a gearbox to drive the two counter-rotating fans. Over the years, the gearboxes have become much more reliable, but we'll come back to that soon. The point is that, thanks to various improvements in design and materials, Safran reported that the noise levels of this engine are the same as those on the very latest CFM LEAP engines. If this is correct, that removes probably the biggest objection to this design. But it turns out that was even more great news to come. I should mention here the excellent work that Björn Ferm at Leham News has done in explaining the purpose behind this evolution in design. If you are interested in this, you have to check out the links in the description below to his work. It is absolutely awesome. Now, it turns out that General Electric, who was already working together with Safran on the 2017 Open Rotor project, had found a way to simplify the design. They had figured out a way to go from a pair of counter-rotating fans to only one single fan with a second set of non-rotating variable incidence stator vanes behind it. That design has now become the basis of the CFM RISE, which stands for Revolutionary Innovation for Sustainable Engines. CFM revealed this project to the public back in June 2021, but it had actually been in the works since 2019, and it really was a continuation of Safran's and General Electric's previous efforts. The move to a single rotating fan from the two counter-rotating fans on all of the previous projects only became possible thanks to new advances in computing and fluid dynamics technology that engineers back in the day could only dream of. And again, development around lightweight but strong fan blades was also crucial here. Having a single rotating fan means that a much simpler gearbox is needed. The kind of proven gearbox design that turboprops have been using for years, and this new layout could also help reduce noise levels even further. According to CFM, the RISE design will meet all current and near future noise level regulations. When it comes to efficiency, expectations around these engines are set really high. The highest bypass ratio of a modern turbofan in a single-aisle aircraft today is around 12:1. But the design of the CFM RISE could allow bypass ratios as high as 20:1. Together with weight savings and other advancements that are part of the CFM RISE project, CFM believes that a 20% improvement in efficiency compared to the best engines that we have on the market today is actually a realistic target. And it goes without saying that it is this 20% improvement that makes this technology so critical for the future plans of both Boeing and Airbus. CFM plans to have an engine ready for ground tests around the middle of this decade. That's just a couple of years away from now. And then flight tests will follow in the second half of the decade. Last summer, Airbus announced that it will work together with CFM by adapting an Airbus A380 test aircraft to complete these flight tests. The CFM RACE will replace one of the 4 turbofan engines under the wing, which will definitely be a really interesting sight to see. It's worth noting here that Airbus is already preparing an Airbus A380 for testing with hydrogen-burning turbofans and hydrogen fuel cells, and there's quite a lot of work needed to add a hydrogen fuel system onto an existing aircraft for testing like that. And this is relevant here because CFM also wants to test the RISE engine running on hydrogen. So having an Airbus A380 that can carry this fuel will come in quite handy. And do you know what else is quite handy? Clicking like and subscribe to this channel so you don't miss any of my future videos. CFM also wants the RISE engine to operate on 100% sustainable aviation fuel, which is a goal for all current and new engines in the next decade. But there are a number of things that CFM will have to show to both aircraft manufacturers and to the aviation authorities before these engines will be allowed to enter service. Obviously, the first thing they're going to have to do is to validate the efficiency of that engine at the promised cruise speed of approximately Mach 0.8. In order to be able to fly that fast, CFM actually had to reduce the diameter of the RISE engine slightly from that of their previous designs. A bigger fan disc pushes more air backwards, but the tips of the fan blades also moves faster, which can be a problem the closer we get to the speed of sound. The smaller overall diameter will also help the aircraft designers a lot when it comes to the engine installation process and options. Previous open fan designs required the engines to be installed at the very rear of the aircraft, like on the MD-80 or the DC-9, which is why Boeing went with this design for the 7J7. But CFM claims that the RISE engine will be suitable to fit under the wing of both high-wing and low-wing airliner designs. Now, there are also a lot of questions of a blade out, which is what it's called when a fan blade breaks for whatever reason. The fan blades of a conventional turbofan are encased in such a way that they will be contained in case of a blade failure, like if the engine would hit a large bird, for example. CFM will now have to prove that this is not a problem for this new design. Of course, manufacturers of conventional turboprop aircraft are already doing this by reinforcing the fuselage alongside the propellers to be able to stop a blade that might have escaped. And we actually have a great example of how that might look like, because during testing in the late 1980s, there was actually additional reinforcement for the vertical stabilizer of the Boeing 727 when it flew with the GE36 instead of one of its normal engines. Newer fan blades will be lighter, which helps, plus these fans will be spinning slower than the turbofans that we have today, but even so, we will have to wait and see what kind of protections aircraft with these kind of engines will need to have. It's likely that these protections will be similar to what we see on today's turboprops. And obviously, additional reinforcements for the fuselage will add more weight. So, who is going to be the first one to incorporate this new engine into one of its designs, do you think? Well, frankly, it's highly unlikely that either Boeing or Airbus will let the other push ahead with a design like this without coming up with a competitor of their own. This technology would be impossible to pass up, so the answer to that question is probably both of them. And Also, let's not forget Embraer, who have recently announced work on a new turboprop with a very familiar looking engine layout. Finally, what is actually the difference between an open fan engine and turboprops, especially in the case of the CFM Rise with its single fan design? Well, the difference here lies in their potential speed. Turboprops generally cruise at speeds of around max 0.55 or so, but the open fan designs will work at speeds around max 0.8, with some having pushed even 0.85 in testing. Now, that's very close to the speeds of today's turbofan aircraft, which I am operating, the 737 for example. But it's also worth pointing out here that the speed difference is not a definition. In reality, turboprops have also been evolving slowly towards the open fan layouts that we've seen in this video. Newer turboprop aircraft have propellers with more and more fan blades, allowing for a higher and higher disk loading, which in turn allowed more and more speed. And also, to be perfectly honest here, the quickest turboprop of all time is not particularly new, because that will be the Soviet Tupolev 95 bomber with 4 turboprop engines using counter-rotating props. It could cruise faster than max 0.8, but the tips of its propellers were supersonic, which made it incredibly noisy. We don't know what the flight crews thought of that aircraft, but there are some stories of fighter pilots who intercepted these planes but couldn't stay close to them for long because of the sheer noise. In any case, I am really looking forward to see what will come of these CFM Rise engines and what they will be able to do. Are we right now seeing the very first stages of a new jet engine war? That might sound like a strange question, since neither Boeing or Airbus have announced any new aircraft designs, and they basically just finished re-engineering their flagship MAX and Neo variants, but that doesn't mean that there is no movement on the engine development side. On the contrary, the case might well be that Boeing and Airbus are basically waiting for the winner of this new engine war before making their own move. Or it could also be the other way around. Stay tuned. In the past few weeks and months, we've been hearing some quite unusual news about issues involving, among others, the engines of the latest editions of the 737 and the Airbus A320 families. And to be perfectly honest, that wasn't completely unexpected. It always takes a bit of time for engine and aircraft manufacturers to learn all the ins and outs of anything new, really, and especially something as complex as new versions of modern turbofan engines. Now, to be perfectly clear here, as a passenger you don't need to worry. The electronic management systems in these new engines is very good, and it would only shut an engine down if it deemed that that would be the most safe option to keep both the passenger's aircraft and the engine in itself safe. Now, it might sound a little bit strange, you wouldn't want your engine to ever shut down itself, but that happening is extremely rare. And in the extremely unlikely situation that one of these engines would decide to shut itself down, well, then all of us pilots are trained to deal with that and to continue to fly the aircraft safely on the remaining engine. But there's no question that there has been some teething issues with these new engines, so let's look at what's going on. To understand this, you first need to remember that the engines that are powering the previous generations of the 737s and the Airbus A320s have been in service for about 3 to 4 decades already. And these trusty engines that we're now talking about are of course the mighty CFM56, and in the case of some Airbus 320s, the IAE V2500. The first CFM56 actually flew as early as back in the 1970s, and today the CFM56 is the most popular commercial jet engine in the world, with over 30,000 of them having been produced up until today. But for the new generations of these single-aisle bestsellers, the aircraft manufacturers needed something new. That's why the 737 MAXes are instead using the CFM LEAP 1 Bravo engines, while the Airbus A320neo operators have a choice between the CFM LEAP 1 Alpha and the Pratt & Whitney Geared Turbofan, or GTF. These are more advanced, but also brand new engines, and as with any new technology, they will naturally need some time before they can achieve the same level of durability as the old tried and tested CFM56 had. But crucially, we're talking about durability here, not reliability, because all of these engines are extremely reliable. So what I mean by the teething problems have to do not so much with actual in-flight faults, but instead mainly with how frequently these new engines require maintenance. At the moment, it seems like these service intervals have turned out to be a little bit more frequent than the airlines would like them to be. It seems like the heat and other environmental conditions that the engines are operating in are a big factor in this, and for that reason both CFM and Pratt & Whitney are currently redesigning a number of parts to improve their time on wing, meaning the time between each time that the engine needs to be taken off, as well as overall durability. But this work is taking some time, and in the meantime some airlines have had to ground part of their fleet simply because they haven't been able to get their hands on spare parts to be able to service their engines fast enough to get them back into the air. And at the moment, the engine maker that seems to be most affected by this is Pratt & Whitney. According to some recent reports earlier this year, as many as 10% of all aircraft in service with Pratt & Whitney's geared turbofans were grounded. Now, this doesn't only affect the airline customers, it also have a knock-on effect on how quickly Airbus, and also to a smaller extent Embraer, have been able to deliver new aircraft to their customers. And that's because Pratt & Whitney have had to divert some of their parts production to the in-service fleet instead of using those parts in the production of new engines. Beside the Airbus A320neo family, other aircraft that are using versions of Pratt & Whitney's GTF are the Airbus A220 and the Embraer E2, who are also suffering from these same delays. The geared turbofan was also supposed to be the engine for the Mitsubishi SpaceJet, which unfortunately was recently cancelled, and until February last year the Russian MC-21 was also supposed to enter service with the GTF, but obviously that is not happening. Now, the airlines who rely on aircraft with these latest CFM and Pratt & Whitney engines are understandably a bit frustrated with these teething issues. So at this point, you might be wondering if it was really worth replacing those engines in the first place. The simple answer to that is a resounding yes, and the airlines are proving this by the extensive use of their wallets. If we look at Pratt & Whitney, for example, despite them suffering much more from these early durability issues than CFM did, they recently announced that they had secured over 800 orders and commitments for its geared turbofan engines, and that was only in the first half of 2023. It really seems like the airlines really want their aircraft to use these newer engines, but why is that? Well, to understand this, we have to look a bit closer at how they differ from the previous engines and why these differences could be leading towards a new engine war with the next generation of engines. If you simply look at aircraft with either CFM LEAP or Pratt & Whitney GTF engines, you might notice that they are larger in diameter than the older generation were. As I've explained in previous videos, to make a jet engine more powerful, the manufacturers really only have two ways of doing that. They can either push the same amount of air out of the back of the engine faster, or they can try to push more air backwards at the same speed. It has been shown that the latter option is far more efficient, so to do this, modern turbofans needs a way to achieve a higher bypass ratio. That's the ratio of air that is driven by the big fan at the front around the engine core versus the air that actually goes through the core part. To achieve this higher ratio, modern turbofan engines have a much larger diameter than the older ones to fit this giant new fan in the front. And on top of that, some, like the Pratt & Whitney GTF, also use a smaller engine core. This has led to engines which are up to 15% more fuel efficient, which is of course what the airlines are really after. But achieving a bypass ratio as high as this also runs into some practical problems. Now, without getting too deeply into the physics of both propulsive and thermal efficiency here, there are two factors in these modern engines that you really need to understand. Firstly, the jet engine engineers want the turbine part in the engine's core to spin really fast, because this will allow them to simplify its design, making it lighter and also more efficient. But conversely, they also want the huge fan in the front to spin relatively slowly, because when that one goes too fast, it starts to lose its efficiency. This has historically been an issue, because the turbine part of the engine is normally what drives the fan in the front. This means that, historically, jet engine designers have had to compromise between the ideal speed of the fan and the turbine inside of the core. But there is a way to let each part of the engine rotate at the best speed possible, and that is through the use of a gearbox or a gear reduction system. Adding this to the construction also adds some complexity, which has taken engineers years to perfect, and it also adds weight, but the extra efficiency is absolutely worth it. So, rotation speed is the first factor you need to understand, and the second is temperature. To get the most efficiency out of the engine core, the engineers needed to enable it to run hot, and I mean really hot. Turbine blades and other engine parts often operate at temperatures that would normally cause even the most advanced metal alloys to melt. And in order to keep that from happening, turbine blades and other parts often had to incorporate various cooling methods into their design. But to make the engine core even more efficient, it would be much better if the internal components didn't need that cooling, or if the engine could be made to run even hotter in some type of way. The physics of this topic are seriously advanced, and if you want to learn more about that part, I highly recommend Björn Färm's work over at Leham News. He is currently running a series on the ways future aircraft and engines will become more efficient and what they will look like. It's really fascinating, you should check it out. So now that we know about the two factors that need to be taken into account in order to make an even more efficient jet engine, then let's look at how CFM and Pratt & Whitney have tried to solve it. In the case of Pratt & Whitney, with its geared turbofan, it's pretty obvious what they've done. You can actually hear it in the name, the geared turbofan. The advanced gearbox that they use in these engines have allowed a bypass ratio as high as 12.5 to 1 in the version used in the Airbus A320neo family. That's huge, and even the A220 and the Embraer E2, who needed a smaller overall engine diameter, still achieved a bypass ratio of 12 to 1, and it's not just the geared fan that made that happen. Pratt & Whitney also spent a lot of effort to miniaturize the core as much as possible in order to further increase this ratio. But what about CFM's LEAP engines then? Well, CFM did not design its LEAP 1 engine family to use a geared turbofan, but even though they didn't, CFM still managed to increase the LEAP engine's bypass ratio compared to the CFM 56 from around 6 to 1 to 11 to 1. These numbers are for the engines used on the Airbus A320 family. The 737 engines needed to be a bit smaller in diameter to avoid them dragging on the ground, so its bypass ratio went from around 5.5 to 1 to 9 to 1, which is still fantastic, but not quite in the same level as Pratt & Whitney managed to achieve with their geared turbofan. CFM did this by focusing their development efforts on the other factor that I mentioned previously, core temperatures. General Electric and Safran, which are the two companies making up CFM, have done a lot of work over the past years aiming to replace parts made of advanced metal alloys with materials called ceramic matrix composites, or CMCs. These CMCs can withstand enormous stresses, vibrations and all kinds of other abuses, which makes them absolutely perfect for the harsh environment inside of a jet engine core. And they can also withstand insanely high temperatures and are considerably lighter than the metal alloys that they are starting to replace. On top of this, there are of course many more advances inside of the LEAP family, including the use of more composites and other clever materials. So even without a geared fan, the LEAP 1 engines can still achieve that 15% efficiency improvement that I mentioned earlier over the CFM 56 engines that they're replacing. So before we continue, let's recap. In the most modern engines that we're using in today's single-aisle aircraft, Pratt & Whitney focused their efforts on miniaturizing the core and perfecting the geared turbofan design. And by contrast, CFM concentrated their efforts on more advanced internal components, so makes the engines lighter and also allows them to run hotter and more efficient. Now, of course, ideally, to be even more efficient than that, a jet engine would need to use both of these technologies together. That would make sense, right? Well, that combination is of course exactly what both CFM and Pratt & Whitney want to do, but in two very different ways. In General Electric and Safran's case, the next project that they are working on is the CFM Rise Open Fan, which I already made a video about a few months back. Like I explained in that video, the CFM RISE project follows much older open fan project by General Electric and Snecma, which is, by the way, what Safran was called back at that time, and also actually separately by Pratt & Whitney. Back in the late 1980s and early 90s, Boeing wanted to replace the 727 and the 737 with a design that they called the 7J7. That design would have made use of this new engine technology. McDonnell Douglas also looked at the possibility of an MD-80 variant that would use an open fan design. Now, what makes these open fans very attractive is that by removing the engine cowling, they can increase the effective bypass ratio much more, potentially as high as 70:1, giving a potential efficiency increase of 20% above the current LEAP engines, which would be insane. But of course, back in the 80s and 90s, the technology just wasn't there yet, neither in materials or aerodynamic modeling, leading to high noise levels due to counter-rotating propellers and also unreliability in the gearboxes. By now, computer modeling has allowed CFM to eliminate that second counter-rotating fan, replacing it with a set of variable pitch but non-rotating blades or vanes to de-swirl the airflow, fixing that huge noise issue. Again, Björn Färm explains this in Leham News in great detail if you want to learn more. But on top of that, now gear reduction systems for the fan are also much more reliable, allowing fans with their new lightweight composite fan blades to work even better thanks to slower rotation speeds. But what about Pratt & Whitney? What are they going to do then? Well, it turns out that for now at least, Pratt & Whitney aren't at all interested in revisiting the open fan concept. Instead, they want to build on their work which they had already done on its geared fan and miniaturized cores by adding the kind of ceramic matrix composites that CFM is already using. Pratt & Whitney wants to use these CMCs to a much greater extent. CFM is currently only using these ceramic composites for the turbine shrouds to its LEAP engines, but what Pratt & Whitney wants to do is to also make these materials for bigger parts, like the turbine blades, for example. This is a project that Pratt & Whitney is working on right now with collaboration from NASA. Remember, CMCs are not just capable of handling super high temperatures, they're also lighter than metal alloy parts, which means that they will be very handy for high energy rotating parts, which is why Pratt & Whitney are looking at them specifically for the turbine blades. Now, to be perfectly clear here, CFM also plans to use ceramic matrix composites in their RISE engine. In fact, General Electric has been testing CMC turbine blades for many years at this point and will probably also use them for larger parts inside of the core. But of course, it's not as simple as just starting to use these new materials. We also have to take into account factors like the very sensitive technology necessary to produce it, both in the right quality, volume and also in price. But what Pratt & Whitney are betting is that their geared fan and other innovations combined with more advanced CMCs will bring enough improvements in efficiency to keep aircraft designers from choosing the CFM RISE open fan, even if they can't match the insane increase in efficiency. And they might actually be onto something with that bet. You see, the CFM RISE engine brings out some question marks, specifically about its installation on the aircraft. It has a really large diameter, so fitting it under the wings of many smaller planes would bring some complications with it. Now, fitting them near the plane's tail will work, but aircraft that have rear-mounted engines generally need a more robust fuselage structure, which adds weight. By contrast, Pratt & Whitney's next engine, when it comes, will still be a turbofan, which the aircraft manufacturers already know how to fit onto their designs. So, does this mean that Pratt & Whitney have a real advantage here? Well, it turns out that it's not that simple. The CFM RISE engine could end up being so much more efficient that even if its installation to the aircraft brings a small weight penalty, it would still be worth it. And even that weight penalty is not a given, because future aircraft won't simply benefit from a new engine design, they might also look different. I recently made a video where we looked at Boeing's and NASA's new transonic thrust brace wing, or TTBW, which by the way has recently been renamed the X66 Alpha. The engines that this aircraft will have when it first flies will be a version of the Pratt & Whitney geared turbofan, but according to John Ostrower in the Air Current, at a later stage Boeing is planning to test this aircraft with the CFM RISE engine. The high-mounted wing of the X66 Alpha, which is a modified MD-90 airframe by the way, should give the RISE engine the necessary clearance that it needs, and Airbus will also test the RISE engine on its A380 testbed. So in reality, whether or not the unique design of the CFM RISE engine will bring a weight penalty in its installation or not, and how big that penalty might be, really depends on what the aircraft will look like. Finally, there is another side to this engine war, which has to do with how engine manufacturers actually earn their money. You see, engine manufacturers earn revenue not just by selling engines, but also by servicing them over their lifetime. So, if these newer engines enter service in the middle of the next decade, as the plan is at the moment, well, then our current newest engines will be less than 20 years old. Could that spell a problem of income for the engine manufacturers who still haven't been able to reap the income from all of those extra juicy years of engine maintenance? Well, that's a very complicated question to answer this early in the process, but there is no question that there are already calls for newer, much more efficient engines as the industry drives towards a very challenging net zero emission target for 2050. One way or another, newer engines are coming, and I am for one looking forward to it. I just operated the 737-8200 for the first time this week, and it was absolutely mind-blowing how low the fuel burn of its new LEAP engines were, and also how insanely cool looking they are. I recently made a video about how the CFM RISE and Pratt & Whitney's geared turbofan would compete to power the single-aisle airliners of the future. But after that video, quite a few of you guys wrote asking, hey, what about Rolls-Royce? Couldn't the UltraFan engine also be a part of this engine war? Well, the answer to that is yes, but it's complicated. Stay tuned. So let's start with having a look at Rolls-Royce history to better understand where they are right now. Rolls-Royce was first established in 1906, founded by Charles Rolls and Henry Royce. Those two partners had already been working together for almost 2 decades at that point, building different machinery and engineering equipment before founding Rolls-Royce in order to make and sell cars. Less than a decade later, with the First World War already underway, the company made its first aircraft engine, called the Eagle, which powered quite a few of the early bombers. But actually, the company went into the aviation business more out of necessity than by choice. Because while Rolls in particular was interested in aviation before the war, the company was doing reasonably well making luxury cars, so there was very little reason to risk that by going into a new venture. But obviously after the war broke up, there wasn't much of a market for luxury cars anymore, so starting to make the pivot into aircraft engines became a natural move to do. Rolls-Royce ended up making over 4,500 Eagle engines in total, and they continued making these type of engines even after the First World War had ended. But it was during the Second World War that their engines became a lot more famous. That was mainly thanks to the fantastic Merlin engine, which was actually the last engine that Henry Royce designed himself, but sadly he never got to see it fly before he died. This awesome engine powered the famous Hurricane and Spitfire fighters, as well as the Mosquito, the Halifax and the Lancaster bombers. In the United States, the Packard Motor Company were given a license to make versions of the Merlin, mainly for the P-51 Mustang, although in the end many of those American-made Merlins actually made it into British fighters and bombers as well. Over 200,000 Merlin engines were made between Rolls-Royce, Packard and other wartime producers, and plenty of those 27-litre V12 Monsters engines are still around today, powering a variety of flying warbirds. Now, Rolls-Royce had started working on gas turbine engines already during the Second World War, designing and making both turboprops and turbojets before the end of the 1940s. And in the 1960s, the company also acquired Bristol Siddeley, another jet engine maker. Now, this was a big deal because it handed Rolls-Royce a number of key engine projects. An example of that was the Pegasus engine, which powered the Harrier jump jet, and the Olympus engine, different versions of which powered the Vulcan bomber and even the Concorde. Between all of their activities, by the 1960s, Rolls-Royce had made engines that powered military planes, tanks, hovercrafts, warships, various industrial applications, and of course several big and small aircraft. In the modern world of commercial aviation, the most important jet engine that Rolls-Royce produced was likely the RB211. This was a very successful high-bypass turbofan that powered aircraft like the Lockheed 1011 TriStar and many of Boeing's 747s, 757s and 767s, and even a few Russian Tupolev Tu-204s. But even though it ultimately became very successful, the RB211 unfortunately ended up bankrupting Rolls-Royce. The company had vastly underestimated how time-consuming and incredibly costly developing this engine would ultimately become. Rolls-Royce went under receivership in 1971, and the British government, who had already subsidized the company to keep it afloat before this, ended up restructuring and nationalizing it. And this, by the way, was the time when Rolls-Royce car and aero engine divisions were separated. It took years before Rolls-Royce could finally start reaping the rewards of the RB211's eventual success, but the company was helped by the fact that a lot of its older turbojet, turbofan and turboprop engines, some going back as far as to the 1940s, continued to be used both in civil and military roles. This meant that these engines needed spare parts and maintenance, which provided a steady flow of revenue for the company even during its darkest times, and that's a point that's worth remembering. Rolls-Royce has since continued to produce new engine designs for various industries, including of course commercial airliners, but when it comes to the future, the direction that the company has taken during the last few decades is now raising some serious questions, including the one that we started this video with. Could Rolls-Royce actually offer an engine for a Boeing 737 or an A320 replacement, an engine that could truly compete with CFM's future Rise open fan or Pratt & Whitney's geared turbofan? And if that is the case, is it going to be the UltraFan that will do it? A major criticism of Rolls-Royce today is that it has missed a really important chunk of the airline market. The company has developed a number of commercially successful turbofans in recent years, most notably the Trent family, whose designs drew heavily from the RB211. Actually, when the Trent was first launched in the late 1980s, it was marketed as an updated, upsized RB211 variant, and the number of aircraft that this engine family has actually powered is quite impressive. Rolls-Royce currently makes versions of the Trent engines for the Boeing 777, the Boeing 787, the Airbus A330, 340, 350 and the Airbus A380. And interestingly, a marine version of the Boeing 777 Trent variant also powers a number of military ships, including Britain's two Queen Elizabeth-class aircraft carriers. Anyway, between the RB211 and the Trent family, Rolls-Royce is covering quite a big variety of airliners. But crucially, with the exception of the long out-of-production Boeing 757, all of these aircraft are long-haul wide bodies. And that turns out to be quite a big problem, because in terms of aircraft production and therefore sales of engines, single-aisle aircraft like the Boeing 737 and Airbus's A320 family outsell widebodies many times over. That's actually why they call the 737s and the Airbus A320s the bread and butter aircraft of Boeing and Airbus. Now, to be fair, Rolls-Royce didn't actually shun the single-aisle aircraft market by choice. Some of its larger business jet engines have also powered some smaller airliners like the Boeing 717, but beyond that, Rolls-Royce also had another significant presence in the single-aisle market. They were a key partner in the AIE V2500 engine project, which provided one option for the legacy Airbus A320 family, the other being the CFM56. The V2500 also powered the McDonnell Douglas MD-90, which preceded the Boeing 717. And more recently, the V2500 was selected to power the Embraer KC-390, which is a military cargo jet roughly the size of a C-130 Hercules. In total, IAE, which stands for International Aero Engines, made over 7,600 V2500 engines, which is a very significant number. Now, originally there were 5 partners in IAE. Rolls-Royce and Pratt & Whitney each had 30% stake, the Japanese Aero Engine Corporation had 23%, MTU in Germany had 11%, and finally Fiat Aviazione held 6%. And given its precipitation in this partnership and the strong sales with the A320 operators, Rolls-Royce felt safe to continue to concentrate on making engines for wide bodies, business jets and helicopters. But the thing was that Rolls-Royce's participation in AIE ended in 2011. In October that year, Pratt & Whitney bought out Rolls-Royce's shares, and at the time, the idea was that Rolls-Royce would eventually join Pratt & Whitney in developing the PW1100G geared turbofan engine, but that never happened. What did happen was that by exiting the IAE joint venture, Rolls-Royce stopped getting a share in revenue from servicing and overhauling those 7600 V2500 engines, and that turned out to be a really big blow. Remember, during previous rough times for Rolls-Royce, maintenance, service and overhaul revenue was really the only thing that had kept some money rolling in for them. So losing a steady flow of cash coming in from the single-aisle airliner market was a truly big loss and potentially a threat in case of a new hit to the aviation market. Now, at this point, it's probably worth explaining a little bit about how jet engine manufacturers actually make their money nowadays. You see, developing and making jet engines is ridiculously expensive. So expensive that realistically, engine makers won't normally get anything even close to a return of that investment simply by designing and selling the engines themselves. No, the profit from developing an engine instead will come over time as the engine goes through maintenance, repairs and overhaul. And important in this story is that Rolls-Royce actually have taken this principle one step further with the introduction of their power-by-the-hour service contracts. What this means is that an airline pays a relatively small upfront amount to purchase the engines for their new aircraft, and instead they then pay Rolls-Royce a fixed amount per flight hour, which includes the engine's service and maintenance. Think of this as a subscription service for jet engines, kind of like how it's cheap to get a new phone as long as you sign up for a long expensive contract with a network company. This actually works great for everyone involved under normal circumstances, because for the airlines this makes their engine purchase and service costs very regular and predictable. And for the engine maker, Rolls-Royce in this case, the agreement assures a steady, high revenue stream and very predictable needs in maintenance personnel, parts and other things. But that also assumes that everything is going according to plan and that the planes are actually flying and building up those billable hours. Obviously, and unfortunately for Rolls-Royce, there has been a couple of reasons why this haven't always worked out in recent years. One reason involves the Rolls-Royce Trent 1000, which powers the Boeing 787. This engine entered service in 2011, but less than 5 years later, engineers found that premature corrosion was causing cracks in the engine's turbine blades. Dozens of aircraft were grounded because of these problems, impacting a lot of airlines and also costing Rolls-Royce billions. As Scott Hamilton explains in Leham News, repairs for these engines forced Rolls-Royce to slow down maintenance work on its other Trent engines, which obviously ended up costing them more time and even more money. And then came 2020, a year that will live in infamy in the aviation world. Obviously, everyone in aviation was hit by the pandemic in different ways, but as I've explained in previous videos, long-haul flying took much longer to recover after the pandemic had subsided. In reality, it took as long as until this year, 2023, so almost 3 years for that to happen. And since Rolls-Royce essentially only made engines for wide bodies and were relying on those power-by-the-hour contracts to get paid, they suffered very badly.
Rolls-Royce, one of the greatest names in British engineering, is the latest major company to reveal the economic cost of the pandemic.
With regards to the future, Rolls-Royce have had yet another bit of bad luck, specifically bad timing. And this finally brings us to the UltraFan. Originally, the UltraFan was planned to be Rolls-Royce's answer to Pratt & Whitney's geared turbofan. It is a completely new engine architecture, which would replace the Trent family, but also give the possibility to be scaled downwards into smaller sizes in order to fit smaller aircraft as well. Now, if it all goes well for Rolls-Royce, the UltraFan might still be able to achieve that. But a few years ago, it actually looked really bright, because Rolls-Royce thought that they already had a customer ready to go, and that would be Boeing. The idea was that the UltraFan would be developed to be used on their new mid-sized airplane, or NMA, which Boeing was planning to launch. This was of course before the 737 MAX groundings completely changed all of Boeing's plans, but we'll get to that in a second. The problem was that Boeing in 2018 and 19 planned that the NMA should be flying as early as 2025, an impossibly tight deadline for an engine to be developed, tested and certified. And it was that 2025 NMA launch date that was the reason that Rolls-Royce cited when they announced that they were actually withdrawing from Boeing's competition to provide an engine for it. Of course, what actually ended up happening was that Boeing later put those NMA plans on ice before ultimately cancelling them in 2020 during their scramble to contain their losses following the 737 MAX groundings. But Boeing's change of plans and the following pandemic meant that if Rolls-Royce now wants to, they should have plenty of time to finish developing the UltraFan engine before Boeing or Airbus have any new aircraft that will actually need it. So, will they? Well, to try to understand that, we have to look at what technologies Rolls-Royce can put to the table compared to what Pratt & Whitney and CFM are already doing with their designs. As I explained in detail in my earlier video on this subject, one key technology is the geared fan, which Pratt & Whitney brought to the single-aisle market first. But General Electric and Safran, who makes up CFM, are applying this technology differently by adopting the open fan architecture of the RISE engine. The other key technology is the use of advanced ceramic matrix composites that enables the engines to run at hotter temperatures and therefore more efficiently. Together with those technologies, Pratt & Whitney and CFM also needs to miniaturize their engine cores as much as possible to help them increase their engine's bypass ratio. So, what is Rolls-Royce bringing to the table? Well, like the other engine manufacturers, Rolls is investing in new lightweight materials designed to bring down the weight of its next engine significantly. The British company is also fitting the UltraFan with a gearbox to drive its fans slower than the rest of the core, so that's very similar to what the others are doing. But as some of you guys pointed out in the comments in my previous video, Rolls-Royce has also pioneered a 3-spool jet engine design. Now, that's a bit too complicated to explain in this video, but it is basically a different way to make the different parts of a jet engine rotate at different speeds by using multiple turbines in the rear to drive multiple concentric shafts. The UltraFan will also have a lean burn combustor system to reduce emissions and fuel burn, and a new configuration of the 3-spool core, which is necessary since the fan at the front now has a gearbox fitted to it. On top of that, when they first announced the UltraFan, Rolls-Royce also mentioned that the engine would have a variable pitch fan system. This would allow its design to be optimized further, and that's actually something that they will have in common with the CFM RISE engine if they choose to go down that path. But sadly, there hasn't been any mention of this variable pitch fan in more recent presentations of the UltraFan, so we don't really know if that's going ahead. In any case, the first UltraFan engine, which Rolls-Royce tested in May this year, had an overall pressure ratio of 70:1 and a bypass ratio of 14:1, which is pretty spectacular. By comparison, the highest overall pressure ratio of any Trent engine is 50:1 and the highest bypass ratio 10:1. But we are not really interested in comparing the UltraFan with previous Rolls-Royce engines. We want to figure out how it might fare against the CFM RISE or the next generation Pratt & Whitney geared turbofan, right? And the problem with doing that is that making an apples to apples comparison is practically impossible in this case. And that's obviously because of the one feature of the Rolls-Royce UltraFan that I haven't mentioned so far. It's absolutely crazy size. At the moment, the world's largest jet engine by fan diameter, which is actually in service, is the General Electric GE9X, which powers Boeing's new 777X. The cowling of that engine is already so huge that it actually has a larger diameter than the hull of the 737 that I fly. Now, the fan diameter of this gigantic GE9X is 134 inches or 340.4 centimeters, and to put that into perspective, the Rolls-Royce UltraFan prototype has a diameter of 140 inches or 355.6 centimeters. In other words, Rolls-Royce, who say that they can scale the UltraFan to fit different aircraft sizes, decided to start the ball rolling by building an engine that is 6 inches or about 15 centimeters bigger than the world's currently biggest airliner engine. So why would they do that? Well, one explanation is that Rolls-Royce wanted to test the most demanding possible gearbox that such an engine might require in order to drive that ridiculously big fan. And to be fair, they did achieve that, Their gearbox is rated at 50 megawatts and reached 63 megawatts in testing. That's about 87,000 horsepower. It is quite possible that when Rolls-Royce decided on the size of their first UltraFan demonstrator, they had stopped thinking about a possible mid-sized aircraft from Boeing or Airbus and were instead concentrating on a direct replacement for their Trent family. Maybe they also had a thought in the back of their mind about providing a possible two-engine solution to the current quad-engine jumbos out there. Who knows? But what this means for our comparison is that we won't know where Rolls-Royce is compared to existing makers of single-aisle engines for a long while. Rolls says that the UltraFan could be scaled to thrust levels anywhere between 25,000 to 110,000 pounds or 110 to 490 kilonewtons. But we know from experience that when an engine is scaled up or down, things like its bypass ratio will also change. The UltraFan's 14:1 bypass ratio is really impressive, but will it stay that high when it gets smaller? Remember, Pratt & Whitney's geared turbofan is at 12.5:1. Anyway, the good news for Rolls-Royce is that the current surge in air travel demand is finally returning it to solid profitability. At the height of the pandemic, they actually planned to put the UltraFan into storage as soon as initial testing was completed, but that doesn't seem to be the case anymore. Rolls-Royce would still need a launch customer for this engine, but being on solid financial footing and with little appetite from Boeing or Airbus for the new airliner for at least the next 10 years or so, it seems that for once Rolls-Royce probably have time on their side to continue working on its concepts. Maybe we will see a scaled down UltraFan eventually. And only then will we be able to know how it stands up to the other competition. Who or what is the biggest threat to Airbus right now, and are they secretly about to release a real revolution? With Boeing in the situation that they are right now, you would think that Airbus would just be sitting back, relaxing and selling planes as fast as they can, but actually it turns out that they can't really do that, because both Airbus and Boeing have another looming crisis to think about, a crisis that won't be waiting for anyone. And that's why, behind closed doors, Airbus are actually working on a brand new aircraft right now. Stay tuned. Now, I have looked at Boeing's recent troubles in a series of videos over the last few weeks, and actually I've been releasing videos about Boeing and its 737 well before the MAX 9 blowout that happened in January. Obviously, in those videos, I have been looking closely at how these Boeing problems will also affect Airbus, and more generally, how these two industry giants compete with each other in this current environment. Now, in one of those recent videos, I focused on how Boeing and Airbus did financially in 2023 and where they find themselves today. But what I actually want to do with this video is to try to look at things from Airbus' point of view and how they are focusing on the future. Boeing today isn't really in a position where they can threaten Airbus in any plausible way, since Airbus has an order book that is both bigger and growing faster than Boeing's. Now, all that actually means is that the disparity between the two aviation giants could actually just grow larger over time, since Airbus could use their higher revenues to effectively outdevelop whatever Boeing does. And of course, that's if the American manufacturer actually decides to develop something new at all. But this doesn't mean that Airbus is completely free from troubles. They are at a much lower scale than Boeing's were, obviously, but the European manufacturer still has plenty of headaches, and these primarily include aircraft delivery delays. Airbus delivered 735 aircraft in 2023, which beat their target of 720 deliveries and obviously eclipsed Boeing's 528, but in 2019, before the pandemic, Airbus delivered 863 aircraft. We actually have to go all the way back to 2017 to see deliveries similarly low as last year's were, so Airbus would like to get back to and obviously supersede those pre-pandemic numbers as soon as possible, but this might still take a couple of years to achieve. In fact, they have recently informed their customers to expect even more delays this year and way into 2025. This is mainly because of problems with their suppliers who are struggling to ramp up those earlier production rates due to looming supply chain issues that just still doesn't go away. But more importantly for this video, these delivery issues should just reinforce what I was saying in the beginning. With Boeing struggling, Airbus has every reason to just concentrate on increasing their production and nothing else. Because they're actually in a situation right now where some airlines at least have started picking the 737 MAX over the Airbus A320neo only because the delivery slots for the Airbus jets are now literally years further down the line than the Boeing jets are. So this should logically be even more reasons for Airbus to just focus on boosting their production and avoid trying something risky like launching an all-new jet, for example. But the thing is that their large order book doesn't mean that Airbus can afford to become complacent. As Scott Hamilton in Leham News pointed out a few months ago, if they're not careful, Airbus could easily make some of the same strategic mistakes that has gotten Boeing into the situation that they are today. You see, the love that Boeing management have shown for financial indications like free cash flow, stock buybacks and general focus on shareholder values are not unique to the American manufacturer. Airbus also does stock buybacks, and some of its organizational changes seem to mirror Boeing's in a lot of different ways. For example, Airbus actually tried to sell off some parts of their aerostructure business in a very similar way that Boeing spun off Boeing Wichita to create Spirit Aerosystems back in 2005. Now, Airbus didn't find any buyers for them then, which I'm sure that they're quite happy about now since they backed away from that strategy. But in other parallels to Boeing, Airbus has also had to deal with quality control issues in their production lines, particularly in Hamburg, Germany, where they have been making nearly all of their Airbus A321neos. Of course, the difference is that Airbus didn't get any quality escapements like Boeing did with the MAX. Instead, those quality problems led to even longer delays. There are also some worries that Airbus have been slipping a little bit with complaints about problematic in-service support, particularly from airlines in the United States. And finally, some airlines have, quite comically actually, been complaining that Airbus are less willing to offer lower prices for big orders now than they used to be. Now, frankly, that's not really a surprise given that their order books are completely full and that they're selling more planes than they're making. Of course, eventually those orders might start to slow down, especially if Airbus successfully increases their production rate. But to be perfectly honest, if I was selling something that was flying off the shelves quicker than I could make them, I wouldn't give out rebates either. But as far as the near future of the European company is concerned, the real jack in the box is the smaller Airbus A220. As the single-aisle demand continues to shift from the Airbus A320 to the bigger A321, Airbus will likely try and expand production of the current A220 lineup and eventually maybe even launch a stretched variant to fully replace the Airbus A320neo. And of course hit Boeing 737 MAX 8 when they do, as I talked about in a recent video. Now that might sound like an easy and logical progression, but let's think a little bit about what that involves in practice. Today, Airbus makes the A320neo family in France, Germany, China and the United States. The Airbus A220, on the other hand, is made only in Mirabel in Quebec, Canada and in the United States, in the same Alabama facility where the A320 is also assembled. So knowing that, how will Airbus actually expand the A220 production enough so that it will replace the Airbus A320? Well, I guess they could eventually convert some of their A320 assembly lines in Germany or France to start making A220s in Europe, but we will probably have to wait to see the answer to that question. It is clear, however, that this won't be an easy transition to do, especially since Airbus have spent decades adjusting their supply chain and assembly sites to the Airbus A320. Crucially though, the fact that Airbus already have an efficient modern jet like the A220 means that the next all-new jet will likely be a little bit bigger than that. Their next jet could coexist with the Airbus A220 and replace the A321neo when the orders for that one starts drying up, likely near the middle of the next decade. Now I know that the middle of next decade sounds far into the future, but if you think about it, it's not too far away at all, especially when you consider how long an aircraft development takes. So what will that aircraft be like then? Well, As it turns out, we recently got a glimpse of exactly the sort of airliner that Airbus has in mind, and it looks frankly awesome. But with that awesomeness also comes some quite serious challenges. Challenges that could actually end up impacting Airbus much more than any competition from Boeing could. On the 15th of December last year, a French politician called Roland Lescure posted a really, on the face of it, boring tweet. Lescure is the French Minister Delegate for Industry, and the post that he made included 4 different images. Now, the first 3 were the kind of stuff that we usually see from politicians: meetings, speeches and group photos. But the 4th image was something much more interesting. It was a rendering, unfortunately at a very low resolution, of an aircraft that we haven't seen before. But when you look at it, this plane was clearly an Airbus and had the kind of livery that Airbus normally uses for showing their future, greener aircraft concepts like the Zero E. And new, greener airliners was exactly what this politician's meeting was all about, which obviously then also included some people from Airbus. Now, you won't be surprised to hear that most people didn't even notice this tiny photo of a plane in this politician's tweet, so my props again goes to John Ostrower and Will Gisborne in the Air Current who sniffed it out. You see, in the past few years, Airbus have been very keen to present themselves as a company that invests heavily in research and development. They have showcased many different projects looking at different areas like wings with flexible wingtips, more advanced composite wing constructions, and of course the Zero E hydrogen project. Now, between them, all of these small projects add up to something that could become the next Airbus airliner, but aside from some interesting hydrogen aircraft renderings, we haven't really seen anything that realistically showed us what this next Airbus airliner would be like, until now. This lower resolution image might well show us the finished puzzle that all of those technological pieces has ended up creating. But the way and the venue where this image was revealed also tells us a few things about the sort of obstacles that Airbus will face if they want to turn this from a concept rendering into a real aircraft. Now, I'll get back to that a little bit later, but let's first have a closer look at this rendering and figure out what kind of aircraft design this is actually representing. First of all, how big is it? Is this just an enlarged turboprop to replace, let's say, a 100-seater jet? Well, actually it doesn't look like it, and we know that because of a feature that we have all talked about a lot lately on Boeing aircraft. If you look closely, this Airbus plane has a mid-cabin exit door with more windows behind them and then another door further back. We're obviously having to speculate a little bit here, but a door like that generally means that this aircraft has seats for more than 189 passengers, possibly even more than 200, unless it doesn't have overwing exits, which aren't really visible in this rendering. But I think it looks like there is at least one overwing exit here, and there's also a hint of markings on the wing to guide passengers out in an evacuation. This would mean either 4 or 5 emergency exits on each side of the aircraft, which would hint at something in the current A320 or Boeing 737 MAX size range. Again, such an aircraft size makes sense if we assume that Airbus sticks with the A220 well after ending the production of the Airbus A320 and 321neo. Because even when the A220 is lengthened, Airbus will still need a bigger plane to replace the Airbus A321. Obviously, the most prominent feature of this new aircraft design are those engines under the wings, or rather under and in front of the wings. And if you are a regular viewer of this channel, I'm sure you already recognize them. And if you're not, it's time to subscribe now. Go on. Yes, these engines clearly seem to represent the CFM Rise, which is an open fan engine design that should be ready for operational use at about the middle of next decade. And that obviously coincides with the service entry date of this Airbus concept. Another feature of this aircraft that is really subtle, at least from this angle, are the shape of the wings. There is a noticeable curve along the length, giving them a gull wing appearance, and this is likely to make it possible to fit those engines under the wing without their blades ending up cutting a trench in the ground underneath them. Because these CFM Rise engines will produce similar amounts of power as the current engines on the 737 or the Airbus A320 families, but the diameter of those open fan blades will be closer to that of a Boeing 777 engine. In fact, they likely won't be far off the diameter of the plane's own fuselage, which will definitely be a quite interesting look to see, but it also means a huge increase in bypass ratio and with that efficiency. But now you might ask, why put the engines under there? Why wouldn't it be better to just put them in the rear where previous open fan test aircraft have had them, like the MD-80 and the 727? Well, the answer here is probably that fitting the engines under the wings makes it possible for the whole aircraft structure to remain much lighter. Airbus could have gone with a high wing design instead, but that would have also increased the weight of the aircraft. This gull wing design will require some additional internal structure, but Airbus must have decided that this is the best overall compromise to enable this engine installation. And actually, some of you might remember that we have actually seen a RISE engine design under a gull wing before. This was during the original presentation of the CFM RISE engine, and you can definitely see a family resemblance between that low wing design and the new Airbus conceptual rendering that we can see here. But this new concept also have other features with clear Airbus lineage. As I said before, Airbus has been experimenting with designs featuring folding wingtips. However, these wingtips won't just fold when the plane is on the ground like on the Boeing 777X. Now, they will of course do that as well, and that in itself is a big deal because it allows the aircraft to still park at the same airport gates as the current A320s and 737s do, while still allowing a wing that is longer overall, giving it a very high aspect ratio. But Airbus has also tested a configuration where the wingtips are then unlocked in flight for load alleviation purposes, or locked at a 10-degree angle for better handling and stall characteristics during takeoff and landing. So why is that important? Well, I've made a video about the concept that Boeing is exploring in collaboration with NASA for an aircraft with transonic truss-braced wings, or TTBW, and with a prototype called the X66 Alpha. Boeing has actually already begun work on this prototype, which was originally an MD-90, and that plane will also have super long, very high aspect ratio wings. But in that case, the truss brace is there to support the structure of the thin, long wing and make it possible for it to support the loads. But from the look of this rendering, it looks like Airbus are hoping to skip the need for that elaborate brace, which comes with its own weight and drag penalties. Instead, it looks like they are going to try to solve the support issue with their super high aspect ratio wing with the help of those flexible wingtips. Now, according to the Air Current, Airbus has confirmed that this is an authentic picture of one of their concepts, but not a definitive one, which of course makes sense. In any case, the name that Airbus will use for its next all-new concept design is the Next Generation Single Aisle, or NGSA, but I'm just going to refer to it here as NAGSA. Now, there is a lot more to be said about this future concept, but the question remains, why would Airbus even bother with it? If competition from Boeing isn't enough to trigger the launch of an all-new Airbus plane, then why are they doing it? Well, the answer is actually quite simple: legislation. And here is where a little bit of that controversy and also that worry that I was talking about before comes creeping back into the story. So, Boeing is working on its own future concept in partnership with NASA, meaning that some US government funds are going into it through the NASA involvement. And if we go back to that tweet from the French minister, we will also find something similar there. Because the topic of that post was a contract between Airbus and the French government for funding towards the development of future carbon-free aircraft. Now, government funding for new aircraft designs is obviously quite a sensitive topic. Boeing and Airbus, and with them the United States and the European Union, have just come out of a really long and costly trade war involving what both sides saw as illegal subsidies.
This is the longest trade dispute in the history of WTO, so it's in our common interest to solve it.
This started in 2004 and didn't end until 2021, with both sides placing tariffs and hindering trade with each other as it was going on. Now, nobody wants to see that happen again, so what kind of money are we talking about this time? Well, Boeing's funding through NASA to develop its transonic truss brace wing prototype is $425 million, divided out over 7 years. And over in Europe, Airbus just signed a contract that will see them and other industry partners and startups receive 900 million euros, or around $970 million over 3 years. Now, this isn't actually an apples to apples comparison, since Airbus themselves aren't getting all of this money. Some of it is going towards development of sustainable aviation fuels, for example, and to be clear, this money is still only a small fraction of what it's needed to actually launch even a relatively conventional new aircraft. And crucially, a lot, actually probably most of this European money is not there to help Airbus design its next new airliner. European governments want to promote carbon-free aircraft, either running on hydrogen or battery electric power, if that technology becomes viable on smaller planes, and some of the funding is going straight there. France has already banned some short flights between destinations that have good, fast train links, and other European countries could soon introduce similar legislation. And that prospect and other initiatives and potential limitations is what Airbus is now regarding as its next challenge, and that's a much bigger challenge than any competition that Boeing could ever mount. The problem for Airbus is that the NAGSA might not be good enough, in this form at least, for the Europeans, unless it's almost completely carbon neutral. But still, if you imagine that it's very likely that between the super efficient new engines and the revolutionary flexible high aspect ratio gullwing, this aircraft could be as much as 30% more efficient than the Airbus A321neo, which would be really revolutionary. Remember, the 737 MAX and the A320neo families are already 13 to 15% more efficient than the previous generation, and that is in itself regarded as a fantastic achievement. But as long as this aircraft is run on normal jet fuel, it obviously still won't be carbon neutral. Now, of course, it could likely run on sustainable aviation fuels, or SAF, which is nearly identical to regular jet fuel and can be made in carbon neutral ways. But wouldn't it be even cooler if Airbus is actually designing this NAGSA as a platform that would eventually transition to a different fuel like hydrogen? As I said before, the colors of the concept in the French minister's tweet are those that Airbus uses for its Zero-E hydrogen aircraft. This concept has passenger windows all the way back to the tail, but what if Airbus designs it so that the rear section, behind the mid-cabin exit doors, could be turned into space for hydrogen tanks, which is something that we have seen on previous Airbus Zero-E concepts. Now, to be perfectly clear, I am only speculating here, but Airbus have pledged that they will introduce a hydrogen-powered airliner in the 2030s. It is quite plausible that, even if Boeing isn't a direct threat to their plans, Airbus are right now designing something that will be a good basis for their aircraft designs that they will be making later on during this century. Something that they could even be scaling up to larger sizes if needed. New engine technology is super important, because if we are ever going to get new airliners to replace the ones we have today, well, then we need newer and much more efficient engines. It's just as simple as that. The CFM Rise is an exciting and very promising engine that could help bring that new generation of cleaner and better aircraft into existence. So today I'm going to answer some of your questions about it and why Boeing now seems a little bit skeptical about it. Stay tuned. Fuel prices have been a headache for the aviation industry ever since the first oil crisis back in the 1970s. But something that many people maybe don't realize is that because of this, the fuel prices have also been directly affecting aircraft designs. For example, turboprop aircraft have often seen a rise in demand for regional and short-haul routes whenever the fuel price have been going up, since they are generally more efficient on those routes, partially due to their lower cruise speeds. But then, as soon as the fuel prices have been dropping again, well, then the airlines have generally been going shopping for smaller jet aircraft instead, since they are faster and also a bit quieter for the passengers. Now, we have all recently also gotten a bit more environmentally conscious, adding yet another reason why we all want to see better fuel efficiency on top of the obvious one for the airlines: money. This is why we have lately seen an increasing call for new, extremely efficient aircraft, and that's only a few years after both Boeing and Airbus actually introduced new versions of their single-aisle jets, who are already 14 to 15% more efficient than the previous generations. Now, as I've explained in previous videos, neither Boeing or Airbus have officially launched any new aircraft to replace their best-selling single-aisle jets, but I have also at the same time pointed to the fact that both of them have been studying something that might eventually fill that role. Airbus, for example, have been working on a group of concepts under the generic name Next Generation Single Aisles, or NGSA, which involves a number of new designs and manufacturing technologies. And Boeing have on their end been working together with NASA on their project called the Transonic Thrust Braced Wing, or TTBW, now officially known as the X-66 Alpha. That's the name that NASA gave the test aircraft that Boeing will build for this project, which is based on an old MD-90, and this aircraft should start test flights as early as in 2028. Now, both of these concepts are looking at different ways of increasing the fuel efficiency by, among other things, improving the design of the airframe, which is basically every part of the aircraft except for the engines. There is a lot to be gained there, thanks to recent access to new lightweight materials, as well as super high aspect ratio wings. Think glider wings, basically. Now, I'll get back to those airframes and their improvements soon, but the reality here is that the by far biggest improvements in aircraft fuel efficiency will always come from the engines. Basically, for a new generation of passenger jets to make any kind of sense, especially for the narrow bodies that make up most of the world's fleets, we need a new generation of more efficient engines. So, what kind of engines can we look forward to then? Well, Pratt & Whitney has his PW1000 Golf geared turbofan family, which is already available in various sizes for different aircraft. Now, they are also looking at developing a second generation of those engines, which I'll also get back to soon. The other engine maker, whose engines power a lot of single-aisle aircraft today, is CFM, which is a 50-50 joint venture between General Electric in the United States and Safran in France. Their latest operational engine is the LEAP 1, which powers a lot of the Airbus A320neo family jets, all of the 737 MAXes, as well as China's C919. And of course, CFM are the ones that's also working on the unique RISE engine, where RISE stands for Revolutionary Innovation for Sustainable Engines. Now, the idea behind the RISE is to increase the bypass ratio of the engine substantially in order to boost its efficiency. As I've explained before, to get more power out of a jet engine, we can either push the same amount of air backwards at a higher speed, or we can push more air backwards at the same speed. And the latter method, more air, low speed, is the more efficient way of doing things. Older turbojet engines pushed a small amount of air really fast backwards, which made them both quite inefficient and loud. Now, a lovely sound in my ears, but it's quite an acquired taste. Now, turbofan engines are like turbojets, except that most of the air is pushed backwards by a large fan in the front, and then it goes around or bypasses the engine core, which means that those engines have what's known as a big bypass ratio. Now, modern turbofan engines, like the CFM LEAP and the Pratt & Whitney geared turbofan, have bypass ratios in the order of 11 or 12 to 1. And the Airbus A320neo version of the Pratt & Whitney GTF actually reaches as high as 12.5 to 1. As far as I know, that's the highest bypass ratio of any operational engine in use today, at least until some version of the Rolls-Royce gigantic UltraFan engine enters service, that is, but we'll see when that happens. But the CFM RISE, thanks to its unshrouded open fan design, will have an effective bypass ratio of around 20 to 1. That's an incredible improvement over the latest generation of turbofans, which are still pretty new, mind you. The potential of this engine design was very well understood already back in the late 1980s, which is why both General Electric and Pratt & Whitney were actually developing versions of these engines already back then. But they both later abandoned the idea, basically because the technology in materials and aerodynamics just wasn't ready yet. And as it turns out, there is still some skepticism around these engines. I actually made a video about the RISE about a year and a half ago, and one of the main questions in the comments back then was, aren't these engines just repackaged turboprops? Why are we going backwards from jets to turboprop designs? Differences between turboprops and open fans. As I often do with technical topics like this one, I'm going to turn to Björn Färm and his excellent work in Leham News. He is right now writing a fantastic series about new engine development, and in that series he's explaining all of these factors in great detail, which I'll link to in the description below. Anyway, in one of his articles, Björn went into some length to explain how propeller designs have evolved alongside engine design in order to make sure that all of the power that the engine produces can be utilized through the propeller at different speeds and speed ranges. Now I'm going to oversimplify this a little bit here, but basically, as engines has become more powerful through history, they started needing propellers with either larger diameters or more blades, or even a combination of both, to really make the most out of all of that power. And as engine development moved forward, the invention of jet engines soon also led to turboprops, which are really just jet engines driving a propeller. But the problem with turboprops was that since they were so powerful, they would require really large propeller diameters to really maximize their potential. And if those propellers got much larger, well, then the tips would start to go supersonic at high power outputs, and that would make them significantly less efficient due to the creation of shock waves at the tips, which would also make them very, very loud. Now, increasing the number of blades instead of increasing the fan diameter could partially solve this problem, and the fact is that turboprops have progressively gone up to 6, 8 or even more blades over time. But even then, the tips of the propeller blades, who actually move both forward and laterally as the propeller screws itself forward through the air, will ultimately move considerably faster than the aircraft itself. And that means that a turboprop flying as slow as Mach 0.6 could actually have propeller tips flirting with Mach 1. So what do you do if you want to cruise faster than, let's say, Mach 0.75 or 0.8 like jet aircraft do? Well, that's when you move from the turboprop to the open fan design, which is designed specifically for these speeds. So in a nutshell, there isn't much difference between turboprops and an open fan. The open fan, prop fan or unducted fan, whatever you choose to call it, is really more of an evolution of the turboprop technology into designs that allows for higher cruise speeds. And if you think of it like that, it's not really a new and untested engine design. It's actually quite well understood. Now, to make these higher speeds possible, the fan blades on the RISE have had to be designed slightly differently than on conventional turboprops. That's why you can see them being swept slightly backwards in order to avoid that premature supersonic flow. And the other thing that has to happen is that they also need to spin those blades slower. To do that, the fan needs to rotate slower than the other components inside of the jet engine, which is accomplished with the use of a gear reduction system, in other words, a gearbox. Now, that's not a huge issue, since we already have turboprop engines with such reduction systems in them, and there are actually plenty of jet engines with geared fans too. As the name suggests, Pratt & Whitney's GTF, or geared turbofan, is the latest one of those to enter service, but actually those type of engines have been around since the 1960s and 70s, although they were quite a bit smaller back then, and initially it also took a while for their gearboxes to get strong and reliable enough to handle airliner-sized thrust levels. But this begs a question. If the latest manufacturer to make a geared turbofan is Pratt & Whitney, then why aren't they using this same technology to make their own open fan design? After all, they tried it 30 years ago with the Pratt & Whitney Allison 578 Delta X-Ray, so why not try it again now when newer materials and more reliable gearboxes are available? Well, this is where I will have to explain why existing turbofans are using gear reduction systems to slow down their fans in the front. And fair warning, we're going to get a little bit nerdy here. Now, bear in mind that a gear reduction system or gearbox suitable for a fan normally needs to be quite heavy, since it also needs to be strong enough to handle a lot of thrust. Remember, most of the thrust from modern high bypass turbofans is generated by the fan, and that means that the fan basically pulls the rest of the engine and the aircraft forward through its shaft and the gearbox that's connected to it. And yet, the Pratt & Whitney PW1100G geared turbofan is actually a little bit lighter than the equivalent CFM LEAP 1 Alpha, which produces more or less the same thrust. How can that be possible when the LEAP engine doesn't have a gearbox and the Pratt & Whitney engine has one? Well, as it turns out, having a big heavy gearbox means that a lot of other parts in the engine can be made simpler and therefore lighter, much lighter. The reason for this is that all modern jet engines are working with a contradicting set of requirements in order to be as efficient as possible. As I said earlier, the fan at the very front needs to spin at a relatively slow speed to offer the best efficiency and the lowest amount of noise. But a lot of other areas in the jet engine must ideally spin at much higher speeds. The turbine, for example, near the rear of the engine, which is spun by the jet's exhaust gases, gains efficiency with speed. And it's the low-pressure turbine stage that drives the fan in the front through a shaft. You see a problem? Without the gearbox between these parts, engine designers needed to figure out how to slow down the low-pressure turbine enough to keep the fan from going too fast. And they have usually done this by adding more and more turbine stages, often giving them larger and larger diameters. The same goes for the low-pressure compressor, who sits just behind the fan. It also needs more stages if it's going to operate at a slower speed and stay efficient. So putting a gearbox between the fan and the rest of the engine means not only that all parts can run at more ideal speeds, but also that the engine can be simplified, reducing the number of turbine and compressor stages altogether. As an example, the CFM LEAP 1 Alpha engine has 3 low-pressure and 10 high-pressure compressor stages, followed by the burn chamber and then the 2 high-pressure and 7 low-pressure turbine stages. By comparison, the Pratt & Whitney geared turbofan also has 3 low-pressure compressor stages, but only 8 high-pressure compressor stages, and then 2 high-pressure and just 3 low-pressure turbine stages. I told you I was going to get a little bit nerdy, didn't I? Don't worry, it's downhill from here, but if you like this kind of stuff, don't forget to click like and subscribe below. I'll wait. So, having fewer compressor and especially turbine stages saves weight, despite the weight of the gearbox. But this is only the beginning. The fact that the fan up front spins slower also means that there is less forces acting on the fan itself, which means that the fan, which is obviously a huge assembly of parts, can also be made much lighter. And it gets even better. Since the fan is both lighter and slower spinning, its blades also have less energy in them. So if one of those blades would happen to break off, well then the fan casing, constructed to kind of contain these blades, will be subjected to less force and can therefore be made less robust, saving even more weight. And I'm sure you can see why that little detail about the fan blades having less energy is also quite relevant to the open fan engine. Yes, the possibility of a fan blade out event is something that many of you asked questions about in the comments on my previous CFM Rise video. So how are CFM going to deal with this problem? Well, first of all, CFM will be using advanced composites to make things like fan blade fatigue cracking extremely unlikely, but they still need to consider blade out events caused by other things, like bird strikes for example. And here comes the good news. As Björn Färm explains in his engine series, the diameter of the CFM Rise is actually very similar to the propeller diameter of an ATR 72's engine. And thanks to lightweight carbon composites, the Rise engine's fan blades won't be any heavier than the turboprop's propeller blades. And since the gearbox is there, the RPM of the Rise engine will also be similar. This means that each of the fan blades of the Rise will have the same or even less energy than a propeller blade on a typical turboprop. So the mitigation and certification strategies to make turboprop aircraft viable, like a slight strengthening of the body next to the propeller, should make the CFM Rise viable too. There could also be more developments to help with this, like frangible composites for the blade tips, and unlike previous open fan designs, the Rise engine has only one rotating fan disc. The rear set of blades are there simply to de-swirl the airflow behind the fan in order to regain about 5% of its efficiency. So then, what are the reservations about these open fans then? Why is Pratt & Whitney not developing one, and what is making Boeing skeptical about it as well? Well, for Pratt & Whitney, the simple answer is that they seem to believe that their geared turbofan engine still has plenty of room for development. An improved version that can make use of advanced high-temperature materials that CFM already uses in some parts of their existing engines could deliver a double-digit percentage improvement over their current engine. And that engine will still, of course, then be a conventional turbofan in terms of how it will be installed, whilst by comparison the RISE engine, at least in the form that we've seen it until now, is obviously a departure from what a typical jet engine looks like. And that isn't just a matter of aesthetics. As I've explained in previous videos, the large diameter of the CFM RISE will have implications on how it can be mounted onto aircraft. CFM has suggested a few different options, but the point is that aircraft will likely need to be designed specifically with this engine in mind. And that means that using these engines will likely come with a bit of a weight penalty. In the case of Airbus, we saw that they are probably planning for a low wing design, which is usually the most weight efficient option since the wing box and the landing gear can then be grouped together. But the Airbus concept that we've seen also has a bent wing with a kind of gull wing shape, likely to make sure that the plane's two engine fans doesn't scrape into the ground. Now, the inclusion of that bend in the wing will incur a small weight penalty, so the extra efficiency of the RISE engine over a geared turbofan will get a slight hit by the need for a heavier airframe. On top of that, even if a broken fan blade has little energy, the aviation authorities will still likely require some of that strengthening of the fuselage that I mentioned before, which would obviously add another weight penalty. And all of these factors put together are known as the installation weight, something you typically want to keep as low as possible. So what about Boeing then? What are they worried about? Well, the interesting thing about them is that their transonic thrust brace wing demonstrator already has a high wing layout, which, like I mentioned, comes with a weight penalty in itself compared to a low wing design. But the super long, extra high aspect ratio of its wing should compensate for that. So in theory, this should make a large diameter engine like the CFM RISE a kind of no-cost option for Boeing in terms of additional installation weights at least. But that's assuming that Boeing is still thinking of the transonic thrust brace wing design as the most likely layout of their next airplane, and if they're having second thoughts about the RISE engine, as Aviation Week believes, then perhaps they're having second thoughts about the aircraft layout too, which I personally think is highly likely because I would love to see how much crosswind that thing will be able to take. There is also another interesting operational consideration when it comes to the RISE engine. According to sources, Boeing has also voiced concerns about the fact that the large propellers on the RISE could cause aerodynamical differences between the flow from the left and right engine, since the deswirling is not 100%, but I personally find that a little bit hard to believe. After having talked to Björn myself, I find it more likely that the airflow from the RISE would interfere with the thrust braces on the wing in a way that causes interference drag, which might make it less efficient compared to a standard ducted design. Finally, Aviation Week also reports that Boeing is actually thinking of offering their next aircraft with more than one engine option, something they haven't done on the 737s ever. Unlike Airbus, who offers two engine types for its Airbus A320neo family, Boeing only offers different engine options on wide bodies like the 787 or older designs like the 767 and 757. If Boeing wants two different engines for the next aircraft, well, then the CFM RISE might be very tough to justify, assuming that the other option is a conventional ducted turbofan. And that's because the turbofan version would obviously have to use the same airframe as the RISE engine version, suffering additional unnecessary installation weight penalties as a result. Having said all of this, CFM has also stated that the RISE engine is a development program that includes more technologies beyond just the open fan design itself. This includes features like the geared fan, the miniaturized engine core, and the extended use of advanced high-temperature materials. All of these innovations will be part of whatever other engines that the company launches in the near future, even if it turns out not to be such a radical new design as the RISE. Now, what do you think? Would you want to fly in an airliner with the CFM RISE engines, and do you think Boeing's next plane will have them? Let me know in the comments here below. it really feels like Boeing just can't catch a break nowadays. Its newest and biggest airliner, the 777X, seemed to be progressing nicely through testing this summer until a new problem stopped it in its tracks.
This morning, Boeing is pausing tests of its new 777X after finding damage to the plane.
So, what happened? What caused the plane's certification program to freeze again? How bad is it? And what's even the point of the 777X? Stay tuned. For some time now, I've been wanting to make a video with an update for you guys on the Boeing 777X project. Now, the reason that I wanted to do that was because there have been quite a few interesting developments in it over the past few months, and most of these have been positive. So the plan I originally had was to make this a feel-good Boeing story. But as it turns out, that just wasn't meant to be.
In another setback for Boeing, the company just grounded its fleet of the 777X test plane. So over the week,
as we record this, the 777X fleet is again grounded, which is doubly frustrating for a program that has been dragging on for such a very, very long time. Just to put this into perspective, the original Boeing 777 was launched in October of 1990. It flew for the first time in 1994, and it then entered service in June of 1995. This means that it went from project launch to carrying paying passengers in less than 5 years. Now, the Boeing 777X is a pretty comprehensive update to the original 777, as I will explain shortly, but even so, you would think that as this is an update, it would be quicker to develop, right? Well, no, not even close. When Boeing launched it in 2013, they thought that the first 777X variant would get certified in 2019 and then enter service either in the same year or in 2020. That's 7 years, so 2 more years than the legacy 777. But obviously that didn't happen. The most recent estimate was that Boeing hoped to get the plane delivered towards the end of 2025 with a service entry in early 2026. If that would happen, it would mean that it has taken from the launch in 2013 to service entry in 2026, 13 years, well over twice as long as it took to get the original 777 up and into production. In fact, just the delays to the program so far are longer than the original 777 development time. And I'm saying so far because these estimates were before the latest problems that were discovered in August. But before I get into that, why is Boeing developing the 777X in the first place? What's the point of it? Well, Boeing designed the original 777 to address a part of the market that, until then at least, was just a small niche. Long-distance flights with relatively few passengers, something that today is known in the industry as long and thin routes. Previously, Boeing had built a smaller version of the 747 for this role, which they called the 747 SP. And while that aircraft made sense for some distance city pairs, it had 4 engines, obviously, meaning that its economics was never good enough to make it wildly popular. Now, Boeing considered updating the 747 SP with newer engines, which they had already fitted to other 747s, but when the airlines rejected that idea, they actually thought of creating a new aircraft with 3 engines, like the McDonnell Douglas DC-10 or the Lockheed L-1011 TriStar. But by that point, Boeing had also gained good experience with their first ever twin-engine widebody, the 767, and there was no question that a twin-engine aircraft would have overall much better economics for all destinations than a similarly sized 3 or 4 engine jet. Boeing also soon figured out that such an aircraft would suit not just these long and thin routes, but basically every route with enough passenger demand to fill the aircraft, and that could potentially open up a whole new segment of long and thin routes. Hence, the Boeing 777 was born. Now, to a lot of us aviation enthusiasts, this aircraft was Boeing's finest hour, and that wasn't just because of its speedy development, which was fast even by the standards of the early 1990s. No, the 777 was also a very advanced design overall. It was, for example, Boeing's first ever aircraft with fly-by-wire controls. Its huge engines were just as new, and it entered service with a, for the time, incredible 3-hour ETOPS approval, which meant that the plane and its engines were thought to be reliable enough to fly huge distances 3 hours away from nearest airport. In later years, the 777 family also grew with a longer fuselage, newer engines and updates to its wing and landing gear. The definitive passenger variant of the evolved 777 family was the 777-300ER, which also has been the best seller of all 777 variants to date. Now, depending on the airline, the 300ER can carry between 350 to slightly over 400 passengers, which means that when it entered service, it was big enough to actually replace its bigger sister, the Boeing 747, for some airlines. But not for all. And that's where the latest generation, the 777X, comes in. The first of these to enter service will be the 777-9, which is about 2.9 meters or 9.5 feet longer than the 300ER. Its higher capacity and range will now make it a direct replacement for the 747, suitable for basically any airline that are still flying passengers with the Queen of the Skies. A smaller variant, the 777-8, will then likely replace the 777-300ER, although it's actually a little bit smaller than the 300. But Boeing doesn't see that as a problem. They expect some of the 300ER users to just choose the bigger 777-9 instead, following the general upscaling trend in the industry. Finally, Boeing is also developing a freighter called the 777-8 Foxtrot to compete directly against the freighter version of Airbus's A350. And in fact, the Airbus A350 was actually a key factor in Boeing's decision to launch the whole 777X program in the first place. You see, Airbus hoped that the Airbus A350-1000, the largest variant of this type, would steal existing uses of the 777-300ER. And initially, Airbus had wanted to make the Airbus A350 by just updating the A330 with a new wing and engines. But the A330 was by then getting old. Its fuselage came from the A300, which had entered service already in the 1970s, meaning that it had already been updated once. So in the end, Airbus went with a completely new design, but by contrast, Boeing's 777 was at that point still relatively new, and its design was really popular with both the airlines, passengers and the pilots. So keeping the 777's fuselage and just updating it with newer engines and a completely new composite wing made total sense if Boeing wanted to compete with the Airbus A350. So essentially that's what the 777X is. A lengthened, re-engined, re-winged 777, a replacement for the Boeing 747 and an answer to the Airbus A350-1000. Now, that new wing that they fitted to it is also quite a bit longer, giving it a bigger aspect ratio, which makes it more efficient, but that's also why it needs those signature folding wingtips. You see, in flight, the 777X has a wingspan of 71.75 meters, or 235.4 feet. But that wingspan would, on the ground, require the 777X to use the same gates as a 747 or an Airbus A380, which are ICAO Category F gates. That would cost the airlines using it a lot more money, and the extra width would also cause some taxiway limitations. The solution? Those cool folding wingtips, which are 3.5 meters or 11 feet long, and when folded, they allow the 777X to use the same ICAO Category E gates, as well as the same taxiways as the existing 777. In order to produce this beast, Boeing built a completely new composite wing facility in Washington State, and General Electric developed the GE9X, a monster of a turbofan engine whose cowling has a larger diameter than the fuselage of the 737 that I fly. But as I mentioned before, Boeing has suffered a lot of setbacks in the project so far. When the Farnborough Air Show opened its doors this year, the only notable exhibit related to the 777X was by Liebherr, who is the maker of those awesome folding wingtips. But at least this time, the absence of the 777X flight display at the air show was for a positive reason. Boeing was finally busy test flying the aircraft with the FAA. At the Farnborough Air Show, Boeing and Qatar Airways announced a new order for 20 new 777-9s. And with these, Qatar now has orders for a total of 60 777-9s plus 34 777-8 Foxtrot freighters. So that was really good news for Boeing, who generally did well at Farnborough. And it also served as a nice follow-up to an even bigger and better story from earlier in July, when the FAA granted the 777-9 with its Type Inspection Authorization, or TIA. The TIA is a list of in-flight tests that an aircraft has to pass successfully in order to prove that it can enter service safely. Basically, the TIA is an extremely detailed checklist which forms a key step in the certification of any new airliner. This process is done by the FAA, with either FAA pilots flying the plane or with each step of the process completed with FAA personnel on board, observing and verifying the process. That was the reason we didn't get to see any of those 777-9s flying over Farnborough this year. They were all busy completing the TIA program. Now, the FAA customizes the TIA program for each aircraft that it evaluates, and that customization is based on the aircraft's characteristics and the new systems or features that is introduced with it. For example, with the 777X, those folding wingtips meant that the FAA had to issue new requirements in order to ensure that the pilots have the necessary procedures to operate them safely. As the Air Current explained in detail, and you should definitely check them out if you haven't already, by the way, before takeoff, the 777X pilots will initially taxi with the wingtips folded on their way out towards the runway. They will then be kept folded until they reach a predetermined point where the taxiways is wide enough to extend the wingtips. And the pilots will obviously also have a wingtips extended check item in their electronic checklist. The process of actually extending the wingtips takes around 20 seconds to do, and if the pilots somehow forget to extend them or there is a malfunction with the system, a warning will light up in their engine indication and crew alerting system, ACAS, to make sure that the aircraft can never take off with the wingtips folded. After landing, the wingtips will start folding automatically once the speed drops below 50 knots, and if that doesn't happen, another ACAS message will tell the pilots to fold them manually. All of these things and procedures have to be tested thoroughly, and the TIA also has to account for things like how the folded wingtips will affect ground handling during strong crosswinds, for example. Obviously, it's normal for new aircraft designs to introduce new features, usually for better efficiency or to improve ergonomics, which is why there's no fixed duration of testing or a specific amount of flight hours to determine when the TIA process can start. The FAA just doesn't begin the process until they are satisfied that the test aircraft is ready for it. And the amount of time needed between the first ever flight of a new type and the start of the TIA flight testing has lately been increasing a lot. According to Aviation Week, which published a very detailed outline of this process, when the original 777 flew for the first time in 1994, it got its TIA just 1 month later, which explains how Boeing managed to get it certified and delivered to customers so quickly. But when Boeing certified the 787 in 2009, the TIA only came after a full 8 months of in-house flight testing. And the 777-9 flew for the first time in January of 2020 and has just got its TIA approval now, 4 years and 5 months later. So why did it take that long? Well, some of you might know that the 777X program had some very early problems with its engines and its fuselage. But to be clear here, those problems happened before even the first flight of the aircraft and therefore shouldn't really have played a role in the delays in getting that TIA. Boeing originally applied for the TIA of the 777-9 in 2021, but the FAA just simply rejected that application since they decided that the aircraft still wasn't mature enough as a design to be ready for it. And why was that then? Well, it was quite clear that the FAA was applying the hard lessons that they had learned from the 737 MAX disasters. So in this case, they were doing a lot of work more directly, rather than just relying on Boeing's own employees. And in this case, it seems like they quickly took issue with several different areas in Boeing's original submission. They were, for example, not happy with the way that Boeing had transferred some systems directly from the 787 to the new 777-9. In theory, this should have been a relatively straightforward thing because the 787 already shared a lot of systems and even a pilot type rating with the original 777, but not so this time. The FAA also wanted to see improvements in the redundancy of some involved systems, and they also wanted Boeing to comply with newer requirements related to human factors and various lessons on behavior of pilots in critical situations. So that process took a lot of additional time, and after the 737 MAX crashes, it wasn't just the FAA that was paying more attention. other regulators around the world were now also closely involved in the certification process, effectively adding their own requirements in some cases. And there is even more to this story, like how Boeing lost even more time when they decided to switch engineers and other resources from the 777-9 to the still uncertified 737 MAX models during the past few years, as their priorities kind of flipped-flop between these two types. But in any case, finally, the coveted TIA came, and Boeing really wanted to get the process right on their first attempt here. That was important because if this FAA flight testing program would go through smoothly, Boeing would probably greatly improve its chances of speeding up the same process with the remaining 777X variants, the 777-8 and the 8 Foxtrot. So they went all in and used 3 out of their total 4 777-9s for these flight tests, switching between aircrafts as the program progressed. And then, on the 15th of August this year, the crew of Whiskey Hotel 003, the third 777-9 test aircraft, landed back on runway 17 in Hawaii's Kuna Airport after a 5.5-hour-long test flight. This aircraft has registration November 779 X-Ray Yankee, and when the test program is over, it is destined to enter service with Lufthansa. But as I'm recording this video, that aircraft hasn't flown again since that last flight, and actually none of the 4 777-9s have. The reason for this was that after the flight, Boeing's ground crew found a broken thrust link connected to one of the aircraft's engines, and that prompted Boeing's engineers to also examine all of the rest of the 777-9 fleet. And unfortunately, during those subsequent checks, Boeing found that there were cracks in more engine thrust links fitted to the rest of the 777-9 test fleet as well. Now, we don't know how many more of these cracks there were, and it doesn't really matter. It's abundantly clear that this is a problem that Boeing needs to both understand and fix. So, what is a thrust link then? Well, this is a structure that is part of how the engine is attached to the wing pylon of an aircraft. Its purpose is to carry the thrust load from the engine itself to the pylon and then on to the rest of the aircraft. I've done many videos on this channel looking at how jet engines work, and in them I have explained that while modern turbofan engines generate some thrust from the exhaust gases coming out of the turbine in the rear, most of the thrust actually comes from the fan itself at the very front. So because the thrust is generated in different parts of the engine, great care must be taken to ensure that those thrust loads created at different thrust levels don't end up pulling the engine apart. Now, here I want you to take a moment to consider just how much forces these engine attachments can be subjected to. Each of the 2 GE9X engines of the 777X generates 110,000 pounds or 489 kilonewtons of thrust, which normally pulls the plane forward. But if one of those engines would go to idle or even shut down while the airplane is at speed, that huge engine will instead start to generate insane amounts of drag, pushing it backwards instead. Or even worse, if an engine eats up a couple of birds when it's operating at a high thrust setting, that can lead to compressor stalls, and that could mean that the engine will go from full power to 0 and then back again many times per second. In reality, all of this is even more complicated because during that brief bang portion of a compressor stall, the fan at the front is actually still spinning and therefore generating some thrust while the core isn't. And of course, there will also be heavy vibrations in basically all directions, which components like the thrust links have to be able to endure. Frankly, I don't even really claim to fully understand all of the complexities of this and the insane engineering behind it, but I think you can see why a part like a thrust link, or actually thrust links, because there's 2 of them per engine, have big roles to play here in order to both keep the engine in one piece and keep it connected to the pylon and the rest of the aircraft. In the case of Boeing's 777-9 in Hawaii, the second thrust link still held up, keeping the engine safely attached to the jet. And the 2 links are mounted at slightly different angles, but they're designed so that each of them can take up the full amount of that enormous thrust load from the engine. And crucially for this story, even though the engines are obviously made by General Electric, the thrust link structure is designed by Boeing. Now, as far as we know, the design of these thrust links is definitely not unique to the GE9X engines. Actually, most of the pictures of thrust links that I've shown you so far are from other engines, like the GE-NX of the 787 or the GE-90 of the original 777. But these two are actually from the GE-9X though. Obviously, the sheer size and power of the new GE-9X engines meant that these parts had to be redesigned, and Boeing are now working on how and why they failed, and also if they need to redesign them. And they have obviously also notified the FAA and their airline customers about this problem and what that might mean. Boy, I am happy I didn't have to be the one that made those phone calls. You see, customers like Emirates, Lufthansa and Qatar really want their 777-9s as quickly as possible because compared to a 777-300ER, the 777-9 burns about 13% less fuel. That's pretty amazing, especially considering that the 300ER itself was around 10% more efficient than the very first 777 that hit the market. But like I mentioned before, some of these airlines want the 777-9 to replace their older 747-400s. And compared to that 4-engine jet, the 777-9 has an incredible 33% lower fuel burn. But until Boeing comes up with a fix for these thrust links, we won't know how much this will further delay the 777X. Time will tell. What do you think though? Let me know in the comments below.